Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And now, for the second session, George will be talking about his adventures in 3D computer vision.
Okay, thanks for inviting me. Apologies for the title. Serious case of writer's block, I think. So the work I'm going to be presenting has been done. Part of it has been done while I was in Toshiba Research in Cambridge University, and at the moment I'm working at Aston. And the outline of my talk is going to be, I'll begin by giving you kind of my sort of point of view on what's happening in the world of 3D vision based on my experience in the past few years. And in particular, what are the key emerging applications, and which of the technologies that are out there are kind of maturing and what are the limitations. And then I'll briefly kind of sketch some simple ideas that we have been pursuing lately. Hopefully to try to overcome these limitations. Okay, so let's move on. There's an ever-growing need for photorealistic 3D models, and this was definitely true when I started my PhD in 2002, but it's even more true now, and I think the reason is because technologies are getting better and better, and I think people just want more out of them. And a 3D model is, of course, just a digital copy of a real object that allows us to inspect details, measure properties, all kinds of physical properties, and if we want to, we can also reproduce using a different material. Okay, so that's basically what this is about. We are looking to extract these types of models. And again, when I started my PhD, I think all of us thought that the big application domain was cultural heritage preservation and the things that go around it, digitizing collections of artworks for museums and galleries and stuff like that. And while there's still a significant number of projects that are doing stuff like that, I think it's becoming more obvious that the real sort of target group for our systems is the entertainment industry, and actually the fundamental user group. And there was a big drive to cross the uncanny valley in face animation, and this was driving a lot of the progress. But as well as developing all kinds of 3D assets for Hollywood or games, the games industry. Related to that, there's also a growing need for the Web 3.0 type applications, and in particular big-scale city modeling. And people are trying to create life-size computer graphics models of urban environments that you can actually kind of navigate in. This is a really cool system, by the way. If you haven't visited it, I strongly suggest it. And then at the same time, there's a drive to bring these technologies closer to the home user. And I've always believed that this is something great. And a nice example of this system has been announced in Cambridge, actually, where you just capture photos of your face and body, upload them, and they will create an avatar that lets you try out clothes virtually and stuff like that. So all of these are actually real, really happening applications, as opposed to things that sometimes researchers tend to think might materialize in the future and they never do. These are actually things that are happening now, and I think it's important to ask, why is vision such a successful sort of approach delivering 3D scanning solutions as opposed to other ones? Because I actually believe that this is actually one of the best examples of computer vision in the real world, right? So why is it successful? Well, I think the reason is because, at least my take on it, is because the traditional approach starts from the real world, and then you have to invest a lot of time and effort to get measurements, laser scanners, spectroscopy, all kinds of stuff like that to measure shape, physical properties. Then you feed this into a model, you compile all these numbers into a model, and then you use machinery and computer graphics, ray tracing, these types of things, to finally generate some visuals for what you want to model. Okay, so this is what the user actually gets at the end. And I think what vision does is effectively it's taking a shortcut out of this whole approach, and basically you start from the real world, but now you just take photographs. It's quite simple, but this is really what it is. and then your model is effectively trying to match the appearance of those images with the visuals that you will be selling to the user at the end. Okay, so by construction, these models are basically designed to be photorealistic because they're trying to mimic reality. Right? There's a plethora of different types of technology exploiting all kinds of visual information to extract shape. However, I think some of them are quickly maturing into real engineering systems. And now I'm just going to sketch the two that I think are kind of good candidates for that. The first one is, of course, the photometric, polarimetric sort of domain of surface capture. People like Paul Debevec, image metrics, all the light stages. That has mostly found use in the high-end film industry type applications. And the results are very, very high quality. But the setup is typically very, very complex and most of the time very expensive, which I guess is kind of good if you're developing these systems, but not very good for adoption. Okay. And on the other opposite end of the spectrum, there's a very low-tech solution, which is multi-view stereo, based around these multi-view stereo technologies. And this is based on capturing 10 to 100 high-res stills, which makes it quite cheap, lightweight, and easily deployed indoors or outdoors. And now we actually have a set of actual software systems that have been developed, starting, I guess, with Yasu system, who I guess started this whole vogue by releasing his stuff for people to publicly try out and experiment and play with. And this caused all these other drives for commercialization and softwareization, let's say. And in fact, the system we developed with Neil, Carlos, Roberto, and myself, has also seen a few commercial implementations, let's say. I have been involved with one for the past 2 years, but I think there have been others as well. The system by the Imagine group in Paris has actually been licensed to Autodesk, and they're giving it out for free. And there's also slightly more professional looking ones, like the software from Agisoft called Photoscan. And you can actually download, I think, a trial version and have a look at that. And all of these things are actually, really delivering the results. They're out there at the moment. However, any practitioner, anybody that has ever tried it, would tell you that the key limitations, there are quite serious limitations, which I think is why some people are giving the software away for free. And one of them is the fact that, we seem to be stuck to this idea of high resolution stills, which I guess, other sensors are presenting very interesting possibilities. For example, video or depth sensors of any form. There was even a workshop at the last ICCV on this type of thing. And another limitation is the type of objects, the type of scenes that can be handled. This is quite a big one. Most people, their biggest annoyance is the fact that it only works on well-textured, granite-looking objects. It will never work on things that are uniform. So for many people, that's a killer. That's a killer limitation. Finally, the world also tends to deform quite a lot. So you somehow need to be able to do something about these deformations, either capture them or be invariant to them of some way. So the rest of my talk will briefly describe 3 simple ideas which we have been putting together, hopefully trying to alleviate some of these limitations. And starting with video, why would you want to do multi-view stereo with video? The answer, to my mind, is the fact that it gives you immediate feedback as opposed to the offline approach of taking the stills. And the feedback tends to lead to better models, and at the same time is also very passive and cheap. On the other hand, to do it, you need online camera pose estimation, which nowadays is sort of readily available. But you need to have a real-time online algorithm, and the key requirement there is interactive rates, and you need to be able to cope with lots of data in the sense of only looking at the data once and not being allowed the multiple passes in the data. Okay, so that's how a video system can scale. Otherwise, it would never scale. So what we did was actually the simplest possible idea, which was to try and treat pixels inside your video sequence as depth sensors. So you freeze a particular frame, you consider a pixel and a 2D box around it. And then with every incoming every incoming video frame from that point onwards, you just do a search along the epipolar line that comes in, compute an NCC score or something like that, and whenever you find the local maximum of that score, just treat that as a measurement coming from this sensor. Okay, of course, you only need to store this little patch, so it's quite scalable to keep these sensors growing. Okay. So hopefully the idea is that you get enough measurements that somehow at some point the correct depth behind this pixel, which is what you're trying to measure, is going to pop out. Okay. And it kind of does. If you actually look at it, this is kind of very hand-wavy type evidence. But if you look at what happens if you have a well-textured pixel, you get two types of measurement. You either get something which is close to the correct depth, or something that is completely uniformly random, based on outliers, on failures in NCC matching of some sort. And of course, if you have untextured or occluded points, as expected, you get a perfectly flat, almost perfectly flat histogram. Nothing kind of stands out. Okay, so that's kind of where we started from, and this type of picture lends itself to naturally to a simple Gaussian plus uniform mixture model for these measurements. And here, Z is the depth that you're trying to infer. Pi is the inlier ratio, which you can also infer, and you just bundle it all up in a Gaussian plus uniform distribution. And we normally fit these things to data using something like EM or similar looking algorithms. But remember, we cannot do it because we need to have a one pass, so not allowed multiple passes. So what we end up doing at the end is sequential inference. And so you basically start with a posterior at time t. You have a likelihood of measurement at time t plus 1. And then you multiply the two together and you get the posterior at t plus 1. Okay? And these are 2D sort of functions, right? Because you have depth as well as the inlier ratio. Okay? So the question was, what form can this posterior take? So you always have the choice of trying a closed form solution, but that's intractable, of course, because the components of the mixture model just grow. The non-parametric approximation, with histograms, is just too memory intensive. It will never be accurate in practice. So what we end up doing, and there's a variational argument in the paper which you can look at, we end up modeling it using a Gaussian times beta distribution. And the Gaussian is for the depth and beta is for the inlier ratio. And the key thing is that this only needs 4 numbers to represent the posterior. And again, for the same reasons, you can't really do the full variational thing. So what we do is we just do a simple moment matching between this Gaussian times beta and this distribution, which is not a Gaussian times beta, it's something different. Okay, so we just moment match in the first 2 moments, and it seems to be working quite well. So I can show you here. So in the top, I have the non-parametric case, which is kind of like my ground truth here. In the middle is the parametric approximation, and this is just histograms. So in the left, you see the successful case where it does work. And you can see that after a while, they converge into each other, and basically they're. And in the failure case, for some reason, because this is approximate, right, and it's not guaranteed to work, it won't work. So it won't get the correct depth and inlier ratio. But it's actually not that bad because it converges into a 0 inlier ratio sort of position, which means that you can discard the sensor as being bad. So it's a nice way to prune away this whole sensor. So now we can build an algorithm on top of this simple idea. And what you do is you initialize a bunch of pixel depth sensors, the way that I described. Then you take a measurement, you update the posteriors, you remove the sensors whose inlier ratio drops below a threshold. And at the same time, you convert into 3D points sensors whose variance in depth drops below a threshold. And at the same time, they're still considered to be inlier generating, sorry. And the final step is you just replace the stuff that you removed or converted into points. You replace them with new sensors in the current frame. Okay. And this is a video of how it works. So you can see the red points are basically the means of the posterior, and the silver ones are when they actually get converted into 3D. So the key requirement is that it's interactive, and you can actually see that you get intermediate representations of the 3D model as it goes on. And if you spot something going wrong somewhere, you go back, you try to fix it. And it's still perfectly passive, perfectly cheap. And the dots are because at that point we hadn't bothered with actually implementing using a SLAM system. I think now it has been incorporated in the system. Okay. So this is, I mean, instead of video, I think you can replace pretty much other depth sensors. I think this is it's, to me, it's quite evident that we need to stop looking at, we need to stop overfitting on the concept of high-res stills. It's not necessarily the best solution. Okay. We did an evaluation that basically shows various things. As the previous speaker said, I won't bother you with that. The really important thing is to have an evaluation with Richard, which we need to coordinate at some point. These are some results. Let me also point you towards work that is done by my colleagues in Toshiba. They are using the system now to do recognition, 3D object recognition, and I think this is going to be more and more important as we move on, because we need to start building higher level models instead of just a soup of points or triangles. Moving on to the next one. As I said, a big grief that people actually have is the fact that these methods don't really work with textureless objects, and that's true even for the video one. So if you can see here, for example, the Tesco soup can is completely empty in all the regions that happen to have no texture in. So what do we do? So when we first saw these types of results, so this is when you apply Yasu's method on this plant data set, okay? And because there's no texture on the leaves, etc., it looks horrible. And so what we thought was, okay, why don't we just try the simple, shape from silhouettes? I mean, even that would be better than that junk. And it is true, because silhouettes can handle lack of texture, and they can also be used by other multi-view stereo methods as well, as kind of as an improvement step, let's say. So if you have them, you should always use them. The problem is that images in the real world are too many, and they have all kinds of clutter in the background, which means that it's actually quite difficult to do a pair image sort of interactive segmentation, because there's just too many images in these collections, hundreds of them or thousands. So bounding boxes, brushes, I mean, all of that is kind of difficult. So our task is basically, let's try and do it completely automatically, okay? So I'll give you a set of post-calibrated images of an object, and you just give me segmentations in all of these views. And now that I think about it, I think this kind of thing might be quite useful for recognition as well as pre-processing steps. So how would you do that? Our previous attempt was using, well, the simplest constraints that you can think of, which is, the first one is silhouette coherence. This concept that visual hull projections have to kind of maximally fill the silhouettes. So you definitely need to use that as a very powerful constraint. Also, we kind of introduce this fixation constraint. This is purely because you need to decide on what it is that you want to reconstruct. So we just assume that it's going to be what the camera is looking. Okay, so if your object of interest is interesting, then you fixate on it. And there's also the appearance consistency, which is standard foreground, background sort of color models, very similar to the ones that GrabCAD is using. But there are limitations, and the key limitation is that this foreground, background sort of color model is actually not separable in space in many situations. One example is the head of this horse here, which you can see zoomed in, and if you plot the color foreground, background likelihoods, it's totally almost blending into the background, right? This is almost like camouflaged. And because of the fact that the horse without the head is quite consistent as well, these algorithms, quite silhouette consistent, these algorithms tend to chop the head off. So then we thought of quite a neat little idea, I think, which is this idea of using a weak stereo formulation, which is just treating the whole thing as a sort of giant MRF problem. Okay, we use superpixels in order to make our life a little bit easier. So you take, you quantize into superpixels, then you do a labeling of each superpixel in your sequence as foreground, background, where the unary term is quite straightforward. It's just the color model that you have obtained in a previous iteration. And the pairwise term encourages pixels to have the same label if they have similar color, if they obey the epipolar constraint, and if other superpixels vote for the same depth. And we plugged all of this thing in an iteration where in each iteration you enforce the silhouette coherence and you keep refining the color models. Okay, so this is the kind of like the weak stereo formulation. And I'll just briefly describe how the algorithm looks like. So in the beginning you do the superpixels. You consider one superpixel, it's almost invisible here, and the optic ray behind it. You project it on neighboring images, and then what you do is you just accumulate evidence for similarity. So it's like a weak form of stereo formulation. And then what you do is for these locations that are seen to be, have quite a few votes in terms of the depth, you just link them. Okay. So maybe in a little bit more clear detail, this is my superpixel. This is the neighboring image, the epipolar line. You calculate one sort of set of consistency scores. Then you get another image. You do it again. Whoops. Yeah. You do it again. And then you just kind of merge these. So these are the histogram versions of the same thing. And then you just combine the histograms. Effectively, every image is voting for depth, and then in the positions that are sort of seen to be to have a high sort of high number of votes, you just link your original superpixel. So if this guy is foreground, then these ones are also kind of encouraged to be foreground, and at the same time you can use this to filter out things that are not don't have much support, so you can increase your sparsity. So it's a almost like the classic sort of version of stereo, only that you have reduced it to superpixels, and you don't really care about the actual depth at the end. You just care about foreground, background. So yeah, I think that's just the same. Copy paste fail. Okay. Whoa. Hope this is not an infinite loop. And this is what actually would happen if you didn't have this depth consistency thing. So you would be linking this superpixel against, well, the correct positions on the head of the horse, as well as other ones that happen to have the same color. Okay, so this is with appearance only. And if you include the depth, you just eliminate all these other positions and you just keep the one you want. And of course it does the horse quite well, but most importantly for me at least, the classic before and after shot, we can now get the plant quite nicely. And one thing I need to mention here is that this is actually surprisingly quite fast. So MATLAB unoptimized stupid code is about a few minutes, basically like 2 or 3 minutes per sequence. So the horse sequence I think was something like 40 images, and it was it's taking basically about 7 seconds per GraphCAD iteration, and it converges in about five or six iterations. So it's quite faster, but much faster than multi-view stereo, which is talking about hours usually. And the final little bit I want to talk about, actually, I'm going to rush through this, I'm afraid, is phase capture. So we had this technique a few years ago based on color photometric stereo, and you just take an image of an object and you illuminate it with different color lights. And the idea is that you can invert the RGB triplet and get surface orientation. Okay, so that's what we had a few years ago, and it was working on kind of white bits of cloth. basically constant albedo. So now, so the key requirement is calibration. When you're doing photometric stereo, you somehow need to estimate light directions and intensities because of the bas-relief ambiguity. And you can either use mirrors, which we have tried, or you can actually use example objects of a known geometry. And in the case of color photometric stereo, what you need to do is basically what we were doing before is just putting the object you want, the cloth, in a pattern and just observing the variability in color. The problem is that with faces, you cannot do that because it's kind of painful to put the skin on a template. So what we end up doing is using an example version of the face, of the geometry of the face, using simple multi-view stereo, very simple motion in front of the system. And I guess the hope is that some parts of the template are going to be good. They have the correct position and normal, but we don't know which is which. So it's kind of like a typical chicken and egg problem. And this basically lends itself to robust model fitting. So basically, the interesting thing here, which I thought was quite cute, was that it ended up being fitting into a 2D homography because you're fitting from the albedo times normal space into RGB triplet space. And of course, we have 2 decades worth of research on 2D homography fitting. And you can use your favorite ransack to do it. Yeah, one thing I didn't mention is that, the key assumption is monochromaticity, the fact that the face is basically different shades of the same sort of color, yeah. And, the lips are not obviously fitting that because they're purple, and the forehead, etc. And this is what the system actually looks like at the end. So the reconstructions of the face. So you can actually see the low frequency error that photometric stereo shows. And a lot of that stuff we have actually kind of fixed, but I don't really have much time to talk about those. Okay, so I just wanted to leave you with a few concluding thoughts. In particular, deformable surface registration is the real kind of problem that you get on top of scanning, and I think maybe the next speaker is talking about that. In terms of the weak sort of shape from X idea, I think it's generally quite applicable, and I think I'd like to see methods that are more kind of quick and dirty, providing quick and dirty solutions rather than doing the full thing, because that's quite useful. And I cannot iterate more this importance of building higher level models that for most users it's actually useless to give them a soup of triangles. What they really want is this is a door, this is a wheel, this is this and that. Okay, so thanks, and can I take questions if we have time?